Hi, I'm Jason Ross. I'm in Beaumont-de-Lomagne in France, the birthplace of one of history's greatest and most underappreciated geniuses, Pierre de Fermat. Fermat is probably best known today for his work in number theory. For example, Fermat's last theorem. Working with Blaise Pascal, Fermat created modern probability. His work in geometry brought him into conflict, a successful conflict, with René Descartes, a very overhyped individual. And his work on method of finding maxima and minima, of tangents and quadratures, this prefigured in a fascinating way the infinitesimal calculus later developed by Gottfried Leibniz. But perhaps the most exciting of Fermat's discoveries, the one that brings him the most into the modern era, was his work in physics, specifically on the refraction of light. While Descartes had published a book explaining the formula for how light bends as it goes from air into water, Fermat figured out why it bends. What's the cause? It's the principle of least action. Among all the paths that light could take, the one that it chooses is the one that gets it to its destination in the shortest time. This principle has become today the principle of least action, and it's the most central concept in all of physics. Join me in an exploration of Fermat's fascinating discovery.
In 1657, Pierre de Fermat solved a problem that had confronted mankind for centuries. He discovered the cause of the way a light path appears to bend as it moves through different substances. We'll return to this principle, known as the principle of least action, later in the video. Now, although Fermat's discovery was unique, the formula for this apparent bending of light, known as refraction, was first published in a book in 1637, with the author listed as René Descartes. For those unfamiliar with this buffoon, the video available at the link below demonstrates the idiocy of Descartes' theory of motion. If you thought his laws of motion were bad, wait till we go through his explanation of light. He actually doesn't even address what light really is. Instead, he uses analogies so that less intelligent people can nonetheless make use of his great insights. He writes that light is not a motion, like the motion of a ball, for example, but instead is similar to the feeling a blind person gets when using a cane. Just as the blind man feels his surroundings to determine whether he is near gravel, cement, bushes, or grass, and feels immediately when his cane strikes something, so too our eyes directly know of sources of light by the action they exert upon us, as though light was a cane pushing on our eyeballs. This impulse moves in a straight line and is instantaneous. Light takes no time to move. So with that clear introduction under our belts, let's see Descartes' explanation of reflection. First, light, which Descartes represents as a moving tennis ball, moves towards the mirror. This is odd, since he had just written that light did not move and was instantaneous, but let's let it slide. Now, when the tennis ball strikes the mirror, the ground by analogy, Descartes uses his brilliant discovery of graph paper to split its motion into two components: motion downwards and to the right. Descartes points out that a tennis ball, simply moving to the right, would never have touched the ground, and would keep moving to the right. Whereas a tennis ball moving directly downward, blocked by the mirror, would have to immediately move upward with the same speed so that none of the motion is lost. Thus, the ball moves to the right just as it did before, and moves upward as fast as it moved downward before, giving this path for reflection. The so-called angles of incidence and reflection are equal. Descartes' explanation of refraction is similar. Here, the tennis ball strikes a body of water and slows down as it enters. But, since Descartes reasons that a ball moving only horizontally would not have touched the water, the horizontal speed of the ball will not change when it does enter the water. Does that make any sense? So he says that if the water causes the ball to lose half of its speed, it can only be the vertical speed which is lost. Descartes draws a circle around the point of impact, remarking, that at half the speed, it will take the ball twice as long to travel the radius of this circle underwater as it did above. But since the horizontal motion continues at the same speed, it will move twice as far to the right in the doubled time. And presto, here you have I, the point that the ball will reach. Now, there's just one problem. Compare Descartes' path to the actual motion of light. As you can see, light bends the other way. That's nothing for Rene to lose his precious sleep over. He simply has to have the ball speed up as it enters the water. Now, that might give the right result, but how could he justify light speeding up, even though nothing else, tennis balls included, does that when it enters water? Well, Descartes writes, and I am not making this up, this is a quote, that as the tennis ball reaches point B, it is struck anew by racket CBE. Where is racket CBE? Maybe it's held by that invisible hand Adam Smith wrote about. Personally, I think this explanation makes just as much sense. Anyhow, he says that the ball, now moving twice as fast, will reach the circumference of the circle in half the time, while the horizontal motion, continuing at its original speed, will only move half as far to the right. And here you have the refracted path and Descartes' formula. Remember, though, that the tennis ball is just an analogy. Descartes says that light doesn't move, but rather that it acts like an inclination to motion, whatever that means. Now, before Descartes could publish his masterpiece, he had to send it to the royal authorities for approval. The royal court councillor sent the book to Pierre de Fermat in southwest France. Fermat, who was busy developing his method of maxima and minima, was less than impressed by Descartes' book, pointing out some errors and writing that Descartes' explanation of light was like groping about in the shadows. He was probably surprised that anybody would publish such trash. The two exchanged a few letters on the subject, but as Descartes became more arrogant, Fermat dropped the discussion. Now, move forward 20 years. It's the end of 1656, Descartes has been dead for 6 years, and Fermat has just received a book from a friend of his, Curot de la Chambre. The book, titled Light, offered a new look at an old idea. He discussed reflection in the same way as Heron of Alexandria in the 1st century AD. Rather than taking the equal angles of reflection for granted, he puts forward a more general principle. The true cause is that nature acts in the simplest possible way. Here you have a point of light emission, a point for the light to reach, and a mirror. What is the simplest path by which the light could have reached the mirror and reflected to the second point? Let's take one possible path, ACB. Now, the total length of this path is not changed if I replace point B with its inverted position below the mirror, B prime. That is, length ACB is the same as length ACB prime. Now, here is a special path, ALB. This path is the shortest path possible. Look, path ALB prime is a straight line, while any other path, such as ACB prime, is not, and is longer. Simple geometry indicates that if ALB prime is a straight line, then the angles of reflection of light will be equal. This simplicity of nature is the principle, and the equality of angles is the result. De la Chambre supported this least action principle, but he was unable to explain refraction, since the path taken by bending light is clearly not the shortest. Fermat realized that the ancient Greek idea was correct, and had the brilliant insight that falsely placing light only in geometric space, but not in physical space-time, was an error. Saying that light took time to move was itself a bold claim, and one that his friend did not agree with. Fermat wrote that light does not move instantly, and that it meets with different resistances to its motion in air and in water. since motion through air is easier, the actual path of refracted light will be longer in the air and shorter in the water, creating a path of least resistance, of least time. Here, two beams of light are heading towards their destination. One takes the direct route, while the other spends more time in the air and less in the water. The path that is shorter in terms of apparent distance is actually longer than the path that seems more roundabout. When it comes to the propagation of light, does it even make sense to speak of distance as measured by a ruler? In light's world, there is no such distance. There is only its action, and it takes the path of least action from among all possible paths. Here, you can see the quickest path flanked by competitors. So how could we determine whether Fermat is right? Since at the time there was no device for measuring light's speed, or in fact whether it took any time to move at all, he couldn't directly time it. Instead, let's determine the exact change in angle corresponding to the least time in tension. Fermat did this with his method of maxima and minima. As an example of Fermat's method, let's take up the problem of finding the cylinder of the greatest volume that can be placed inside a sphere. There are a whole series of cylinders, from squat like a pancake to thin as a pencil. Fermat took all of these possible cylinders and grouped them 2 by 2. Each cylinder has a twin with the same volume as itself. This is a series of twins, with the volume represented by the cylinder in the center. Did you notice anything special about the greatest cylinder? It is its own twin. Fermat's method states that a maximum or minimum always has this characteristic of being its own twin. So let's apply this method to paths of light. Each path of light, bending when it enters the water, has a twin. By pulling these twins together until we have the path that is its own twin, we discover the path of least time. The equations and math themselves take some work, and Fermat delayed doing that for 5 years. When he did, he was shocked at what he found. But the reward of my work was more extraordinary, more unforeseen, and happier than ever. For after having run through all the equations, multiplications, antitheses, and other operations of my method, and having at last solved the problem, as you will see on a separate sheet, I found that my principle gave exactly and precisely the same proportion of refractions that Monsieur Descartes had established. I was so surprised by such an unexpected outcome that I had difficulty coming out of my state of astonishment. I repeated my algebraic operations many times, and always the success was the same, even though my demonstration assumes that the passage of light through dense bodies is more retarded than through rare ones, an assumption which I find quite true and indisputable, and yet Monsieur Descartes assumed the contrary. So what did Fermat think of Descartes' supposed discovery? It seems that this great truth of nature did not dare to stand up against this great genius, and that it surrendered to be discovered by him without being forced to do so by a demonstration. Like a castle, which, although well fortified and defended, surrendered upon hearing the reputation of the attacker, without a single shot being fired. This is classic Fermat, offering humorous insults in language that sounds like a compliment. As Fermat advocated his principle of least time, the Cartesians became enraged. Descartes' intellectual heir, Claude Claircellier, shrieked,
"The principle that serves as foundation for your demonstration, namely that nature always acts by way of the shortest and simplest paths, is but a moral principle and not at all physical, which is not and could not be the cause of any effect of nature. It is not, because it is not this principle that makes nature act, but rather the secret force and the virtue that is in each thing, which is never determined to a particular effect by this principle. and it could not be a cause, because otherwise we would assume nature to have knowledge. But by nature, here we mean only that order and that law established in the world as it is, which acts without foreknowledge, without choice, and by a necessary determination.
So, according to the Cartesians, a secret force and imaginary tennis rackets do express nature physically? To torment mankind's foes, Fermat gave them a taste of their own mathematical medicine, posing a scenario in which a ball hits a surface and loses half of its speed while not passing through it. Using Descartes' mathematical rules, you can see the results. The ball bounces off the mirror at an unusual angle. But what happens as we increase the incoming angle? Here, the horizontal motion is half of the total speed, so that when the speed is cut in half, the entire vertical motion vanishes, and it just rolls horizontally. What would happen in this case? Fermat writes that he has put Monsieur Descartes' ball in an uncomfortable situation. You might be wondering, how did Descartes get his formula in the first place? Well, in Holland, Willebrord Snell had discovered the formula for light refraction before Descartes, and he was a professor of mathematics at the University of Leiden, shortly before Descartes himself attended the same university. Here's what Leibniz has to say.
The demonstration which Descartes sought to give of this theorem is not nearly as good. Indeed, there is room to suspect that he would never have found it by this method had he learned nothing in Holland of Snell's discovery.
Descartes is like a student cheating on a test, who has copied the answer from a classmate and then scribbles something to get full points for showing his work. How could anyone respect René Descartes? In addition to differing about whether light speeds up or slows down in water, there is a huge difference in approach between the two. Descartes starts with an idea about how a single beam of light might act in empty space, saying that it moves in a straight line. And then he alters this universal quality by adding changes when light moves through different substances. That is, for Descartes, reality is an exception to his principle. Fermat makes no such statements about a single independent ray of light, because it does not exist. When does light propagation, or anything else for that matter, when does it ever occur outside of a context? Or, where is space empty? Let me ask you, does light ever move in a straight line? When it is only in the air? Nope. The atmosphere bends light, which is why astronomers very much wanted to understand refraction. Let's stay close to the Earth's surface. Is there some place where air is totally uniform? Maybe in water. Again, temperature and salinity differences disturb the path of light. Okay, how about in the vacuum of space? Einstein says no. Light never moves in a straight line. The mechanical approach starts by defining the activity of pieces and builds up a whole from them. Fermat's approach, like Kepler's approach of harmonics, seeks to understand the process as a whole. While Descartes would have to fill space with innumerable tennis rackets, constantly adjusting light to veer from what he considered its natural straight line path, Fermat has a single principle that entirely determines the activity. For Fermat, the moment that light passes from one substance to another is no longer an event at all. It is always wrong to seek to understand a process by breaking it into pieces that cannot exist independently, and then trying to determine the characteristics of these independent pieces. Not only is the whole greater than the sum of such parts, these parts do not even exist. Although Fermat discovered least time in the macro scale, further development of the principle of least action treated it as an infinitesimal principle. This can be seen in the work of Leibniz, of Gauss on geodesics and anti-Euclidean geometry, of Riemann, and in Einstein's general theory of relativity. A full understanding will require the approach of Vernadsky and bringing the study of the biological and cognitive realms into the investigation. The previous video in this series, Dynamics and Vis Viva, introduced Leibniz's approach to science. Everything, even simple motion, must be understood in terms of the future that it brings about. Now, with Fermat's principle of least time, we have an excellent viewpoint to understand the difference between a credit system and a monetary system. Monetarism treats the economy the way Descartes does. Individual economic participants decide what is valuable to them for their personal pleasure, and this then determines prices and drives supply to cater to present inclinations. Adam Smith was explicit about this, saying that God moved society forward by these base motives.
Hunger, thirst, and the passion which unites the two sexes, the love of pleasure and the dread of pain, prompt us to apply those means for their own sakes, and without any consideration of their tendency to those beneficent ends which the great director of nature intended to bring about by them.
This is the rejection of reason. Planning for the future is ruled out, and personal happiness is artificially constricted to the sorts of pleasures that Smith would likely enjoy. This is a political theory, not an economic one. It tells people to stay out of political planning and to enjoy base pleasures instead of ideas. Under a credit system, reason prevails. Value is understood with an eye to the future, and no economic activity can be judged or valued outside the context of the future that it is helping to bring about, or hindering. Rather than atomized individuals seeking to maximize their individual pleasures, a society can organize itself around a mission. Let us adopt the mission of building the NOAPA project and developing fusion-powered spacecraft capable of moving to Mars in a week. With such an outlook, it is possible to look at individual people as they truly are, participants in a developing process. With that outlook, how could anyone tolerate windmills, casinos, or bank bailouts as economic policy? Who would accept creating policy as a response to current crises instead of future goals? The importance of LaRouche's proposed credit system does not lie in a different mechanism of currency transfer, but in epistemology. While monetarism ruts about in the past, a credit system draws the present towards the desired future. Thus, the future intention shapes present activities, just like Fermat's light. Today, a global Glass-Steagall approach to separate good debt from bad, emergency credit, and international credit agreements for physical economic development are absolutely required to avert an economic catastrophe greater in scale than the European Dark Age. I ask you, when it comes to society, will you let present inclinations determine the future? Or will the vision of a desired future guide your present actions? Think about it.